The morning of August 3rd, 1942, Philadelphia Navy Yard. A warehouse holding 43,000 herringbone twill uniforms, each one printed with America's first camouflage pattern. They should have shipped to Marine raiders in the Solomon Islands 3 weeks ago. Instead, they sit in stacks that reach the ceiling, useless. Walk closer, and you'll see why. The green jungle pattern on one side has bled into the tan beach pattern on the reverse. The colours have run together like watercolours left in the rain. 43,000 uniforms, every single one rejected by quality control. Every single one representing a Marine who will land on Guadalcanal wearing plain olive drab, visible to every Japanese sniper in the tree line. Have you ever watched something you built with your own hands fail spectacularly? Not because you did it wrong, but because the method itself was fundamentally broken. That moment when you realize the entire approach needs to be thrown out and rebuilt from scratch? That's where American camouflage production stood in August 1942. The designs looked perfect on paper. The concept was sound. But translating those designs onto fabric at the scale and speed the war demanded? Nobody had figured that out yet. And without camouflage, American troops were dying in numbers that made generals sick. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem started 6 months earlier when General Douglas MacArthur sent an urgent request from the South Pacific. 150,000 sets of jungle camouflage uniforms, needed immediately. The Marine raiders were about to launch offensive operations in the Solomon Islands, dense jungle terrain where olive drab uniforms made American troops stand out like targets at a shooting gallery. The Army Corps of Engineers had been experimenting with camouflage patterns. Since 1940, a horticulturist named Norvell Gillespie had designed something called the frog skin pattern, inspired by studying how frogs' mottled skin helped them disappear against leaves and rocks. 5 colours on one side, green dominant for jungle. 3 colours on the reverse, tan dominant for beaches, reversible, clever. Perfect for the Pacific where one island might be pure jungle, the next one a sandy atoll. But Gillespie was a designer, not a manufacturer. He could draw the pattern. He could specify the colours. What he couldn't do was explain how to print it onto 50,000 yards of herringbone twill fabric per week without the colours bleeding, fading, or smearing into an unusable mess. The Quartermaster Corps sent the approved design to 3 textile mills, 2 in Pennsylvania, 1 in Massachusetts. These mills had been printing decorative fabrics for decades. Curtains, upholstery, dress materials. They used a process called flat screen printing, stretched with silk mesh. Block out certain areas with lacquer. Force ink through the open mesh onto fabric below. 1 colour at a time. Dry it. Print the next colour. Simple. Reliable. Completely inadequate for military camouflage. Here's why. The frogskin pattern required 5 colours on the jungle side alone. Light green, dark green, brown, tan, black. Each colour needed its own screen. Each screen had to align perfectly with the previous one. Registration within 1/32nd of an inch, or the pattern would look blurred and amateur. And each colour needed 2 hours to dry before you could print the next one. 5 colours meant 10 hours of drying time per fabric length. Then you had to flip the fabric and print 3 more colours on the reverse side. Another 6 hours. 16 hours total to print both sides of a single piece of fabric for 1 uniform. The math was brutal. To produce 150,000 uniforms meant printing fabric for at least 300,000, separate pieces, jackets and trousers. At 16 hours per piece, working round the clock with perfect efficiency, you'd need 4,800,000 hours of press time. That's 547 years of continuous production on a single printing press. The mills tried running multiple presses simultaneously. By July 1942, they had 23 flat-screen presses dedicated to camouflage printing. They should have been producing 5,000 uniforms per week. They were managing 300. And half of those failed quality inspection. The bleeding problem was the worst. Herringbone twill is a dense cotton weave, but it's still porous. When you print wet ink onto fabric, some of it soaks through to the reverse side, especially if you're using the heavy ink load needed for military durability. Print green on the front, and faint green stains appear on the back, muddying the tan beach pattern. Print all 5 jungle colors, and the reverse side looks like someone spilled paint. The mills tried thinner inks. The colors faded after 3 washings. They tried slower drying inks. Production dropped to a crawl. They tried barrier coatings between the front and back printing. The fabric became stiff as cardboard, unwearable in tropical heat. By August, the situation had escalated beyond industrial problem into strategic crisis. Marines had landed on Guadalcanal on August 7th, wearing plain utilities. Japanese snipers, concealed in camouflaged positions, were inflicting casualties at rates higher than any previous Pacific engagement. Radio intercepts showed Japanese soldiers joking about how easy it was to spot American troops against the jungle backdrop. War Production Board representatives visited the Philadelphia mills on August 12th. They watched the printing process. They examined the rejected uniforms. They did their own math and reached the same conclusion the mill operators already knew. Flat screen printing couldn't scale to meet wartime demand. Not even close. What they needed was a completely different approach. Something that could print multiple colors simultaneously. Something that could handle fabric moving continuously through the press instead of stopping and starting for each color application. Something that could maintain registration across all colors without human adjustment. That technology existed. It was called rotary screen printing. Instead of flat frames, the screens were formed into cylinders. The fabric moved continuously beneath the rotating screens, each cylinder printing one color. No stopping. No repositioning, just continuous, high-speed production. There was only one problem. Rotary screen printing for textiles didn't exist in America in 1942. The Dutch company Stork had been developing the technology since the 1930s, but their work had been interrupted when Germany invaded the Netherlands in May 1940. The equipment, the technical knowledge, the manufacturing expertise, all of it was trapped behind enemy lines or scattered across occupied Europe. American textile engineers knew rotary printing worked for wallpaper and wrapping paper, but fabric printing required much finer detail, more precise registration, different ink viscosity. Nobody in the United States had solved those problems. Nobody except possibly one man, and he wasn't even a textile engineer. His name was Samuel Berman. He was 51 years old. He'd spent the last 20 years running a small specialty printing shop in Brooklyn, mostly producing circus posters and theatrical backdrops. Before that, he'd worked in his father's tailor shop in Manhattan's garment district, stitching linings into wool overcoats, watching fabric move through industrial sewing machines at speeds that seemed impossible for such delicate material. Berman didn't solve the camouflage crisis because he was smarter than the textile engineers. He solved it because he asked a different question. Everyone else was asking, "How do we print this pattern faster?" Berman asked. "How do we stitch this pattern instead of printing it?" The afternoon shift at Philadelphia Quartermaster Depot, September 14, 1942. Rose Kellner stands at flat screen printing station number 7, watching another batch of herringbone twill fabric crawl past her squeegee at a pace that makes her want to scream. 3 yards per hour. That's it. 3 yards. Her station prints the dark green layer of the frogskin pattern. 5 stations down, Martha prints light green. 8 stations beyond that, someone else applies brown, then tan, then black, each color requiring 2 hours to dry before the next layer touches the fabric. Each worker waiting, equipment idle, while chemistry does its glacial work. The Marines landing on Guadalcanal needed these uniforms 8 weeks ago. They're fighting in olive drab that makes them visible from 200 yards. Japanese snipers are having target practice. And Rose is printing fabric at a speed that wouldn't outfit a single rifle company before Christmas. Do you know what it feels like to work as hard as humanly possible and still fail? To watch the numbers on the production board fall further behind every single day, no matter how many extra shifts you pull? That's what every worker at the Philadelphia depot felt in September 1942, the invisible weight of soldiers dying because factories couldn't move fast enough. The problem wasn't effort. Everyone was working double shifts. The problem wasn't skill. These were experienced textile printers, some with 20 years at their trade. The problem was the method itself. Flat screen printing, the dominant textile printing technology since the 1880s, simply couldn't handle the complexity and speed that modern warfare demanded. Here's what flat screen printing involved. A wooden frame, typically 4 feet by 6 feet, stretched with fine, silk mesh, areas blocked with lacquer where you didn't want ink, open mesh where you did. You positioned the screen over fabric, poured thick ink paste onto the mesh, and dragged a rubber squeegee across the surface. The squeegee forced ink through the open mesh onto the fabric below. One color, one pass. Then you lifted the screen, moved the fabric forward exactly the length of the repeat pattern, and printed again. Each screen had to align perfectly with the previous color layer, registration within 1/32 of an inch, or the pattern looked blurred and sloppy. For simple patterns, 2 or 3 colors, the method worked fine. Department stores sold millions of yards of flat-screen printed curtains and dress fabrics every year. But frogskin camouflage required 5 colors on the jungle side, 3 on the beach side, 8 separate printing operations, 8 opportunities for misalignment, 8 drying cycles. And the drying was killing them. Ink needed to set completely, before you could flip the fabric or apply the next color, otherwise everything smeared together into an unusable mess. Standard drying time, 2 hours per color layer, sometimes 3 hours if humidity was high. The math was impossible. One uniform required approximately 6 yards of fabric. To print 6 yards through 8 color layers with 2-hour drying between each meant 19 hours minimum from blank fabric to finished camouflage. 19 hours for one uniform. The Marines needed 150,000. By October 1942, 3 textile mills were running dedicated frogskin production: Philadelphia Quartermaster Depot, Riverside Mills in Rhode Island, and American Silk Mills in Pennsylvania. Combined, they had 42 flat-screen printing stations operating 24 hours a day. They should have been producing 8,000 uniforms per week. They were delivering 900. And quality control was rejecting 40% of those for color bleeding, misregistration, or pattern defects. Colonel James Harrison, Chief of Textile Procurement for the Quartermaster Corps, visited Philadelphia on October 22nd. He watched the printing operation for 6 hours. He examined rejected fabric that showed green jungle colors bleeding through to the tan beach side. He talked to exhausted workers who'd been pulling 12-hour shifts for 3 months straight. Then he went back to his office and wrote a memo that would never be declassified until 1978. The subject line read, "Assessment of Camouflage Production, Crisis and Alternative Manufacturing Approaches." The memo laid out the problem with brutal honesty. Flat-screen printing technology could not scale to meet wartime demand. Not with 500 additional workers. Not with 50 additional printing stations. The bottleneck was inherent in the sequential nature of the process. You couldn't parallelize it. You couldn't speed up chemistry. You were stuck. Harrison proposed 3 options. First, abandon reversible camouflage and switch to single-sided printing with 4 colors instead of 8. This would cut production time in half but eliminate the beach pattern, making the uniforms less versatile. Second, accept lower quality standards and ship uniforms with minor bleeding and misregistration. This would increase yield, but might compromise concealment effectiveness. Third, investigate rotary screen printing technology. That third option was the interesting one. Rotary screen printing had been developed in Europe during the 1930s, primarily in the Netherlands by a company called Stork. Instead of flat frames, the screens were formed into cylinders roughly 18 inches in diameter. The cylinders rotated continuously, while fabric moved beneath them at speeds up to 100 yards per minute. Each cylinder printed one color. Multiple cylinders could be arranged in sequence, applying different colors without stopping the fabric. Drying happened between cylinders using hot air blowers. The entire process was continuous. No stopping, no repositioning, no waiting. American textile engineers knew about rotary printing. Several mills had imported experimental equipment in the late 1930s for printing wallpaper. But fabric printing was different. The registration requirements were more stringent. The ink viscosity had to be precisely controlled. And most importantly, nobody in America had successfully printed multicolor patterns on fabric using rotary screens. The equipment existed in theory. The expertise didn't, at least not officially. But Harrison had heard rumors about a small printing operation in Brooklyn that might have figured it out. A specialty shop that produced theater backdrops and circus posters. The owner, a man named Samuel Berman, had supposedly built his own rotary printing system using modified wallpaper equipment. Harrison sent an investigator to Brooklyn in early November. What the investigator found was half genius, half insanity. Berman's shop occupied a converted warehouse near the East River. Inside, a massive contraption filled most of the floor space. 3 cylindrical screens mounted on a steel framework. A fabric feed system cobbled together from industrial sewing machine parts. Pneumatic squeegees inside each cylinder, activated by compressed air. The whole thing looked like something a mad inventor would build in his garage. But it worked. Berman demonstrated by printing a 3-color theatrical backdrop in 17 minutes. The same job would have taken 6 hours on flat screens. The investigator asked how Berman had learned to build rotary printing equipment. Berman explained that he hadn't learned. He'd invented it out of necessity. Before the war, his business printed large-format posters and backdrops for Broadway theaters. Flat screens couldn't handle fabrics wider than 6 feet. He needed 12-foot widths. So he took a wallpaper rotary printer, modified the cylinder diameter, adjusted the squeegee pressure, and experimented with different ink formulations until he could print on theatrical scrim without bleeding or distortion. It took him 3 years and nearly bankrupted his business. But it worked. Harrison brought Berman to Philadelphia on November 18th, showed him the frogskin printing operation, showed him the rejected fabric, asked him one question. Can you build equipment that prints this pattern at commercial scale? Berman studied the pattern for 20 minutes. He examined the ink viscosity. He tested the herringbone twill fabric for porosity and dimensional stability. Then he gave an answer that nobody wanted to hear. Not with flat screens. Never. The drying bottleneck can't be solved. But rotary screens printing continuously with forced air drying between stations? Maybe. Probably. If I can solve 3 problems. Problem 1, registration. Flat screens could be manually adjusted if colors didn't align. Rotary cylinders couldn't. Once they were mounted and rotating, you either got the alignment right or you didn't. Berman estimated they'd need registration accuracy within 0.05 millimeters across a 3-meter printing width. No American manufacturer had achieved that. Problem 2, ink bleeding. Printing wet ink onto fabric that's moving at 60 yards per minute meant ink had less time to absorb before the next color hit. If they couldn't control penetration depth, the jungle colors would bleed through to the beach side worse than flat screens. Problem 3, cylinder fabrication. Each color required its own cylinder screen. The frogskin pattern needed 8 cylinders. Each cylinder had to be perfectly round, perfectly balanced, with thousands of microscopic perforations in exactly the right pattern. One cylinder cost approximately $800 to manufacture. 8 cylinders, $6,400. Per printing machine. The Army needed at least 6 machines to meet production targets. $38,000 just for cylinders, assuming they got the pattern right on the first try. If they had to remake cylinders due to registration errors or pattern problems, costs could easily double. Harrison made a decision that bypassed normal procurement channels entirely. He authorized Berman to build one experimental rotary printing line using War Production Board Emergency Manufacturing Authority. Budget, $50,000. Timeline, 8 weeks. Success criteria: print 100 yards of frogskin fabric per hour with less than 5% defect rate. If Berman succeeded, they'd order 6 production machines and train mill workers to operate them. If he failed, they'd abandon rotary printing and accept that camouflage production would remain slow and inadequate for the duration of the war. Berman started work on November 25, 1942. He rented factory space in Camden, New Jersey, across the river, from Philadelphia, hired 12 machinists from closed automotive plants, ordered steel, pneumatic cylinders, compressed air systems, fabric tensioning equipment. The cylinders were the hardest part. He needed them manufactured by a company called Stork in the Netherlands, the only fabricator in the world with the precision equipment to create seamless rotary screens. But the Netherlands was occupied by Germany. Stork's facilities were producing fabric for Wehrmacht uniforms. Berman found a workaround. A Stork engineer named Henrik van der Meer had escaped to England in 1940 and was working with British textile manufacturers. Van der Meer had brought technical drawings and manufacturing specifications. He couldn't make cylinders himself, but he could teach American machinists how. By December, Berman had van der Meer in Camden, training workers to hand fabricate rotary screens using techniques that would normally require industrial electroforming equipment. They started with copper cylinders, electroplated them with nickel, then used a photo engraving process, similar to printed circuit board manufacturing, to create the perforation pattern. Each cylinder took 3 weeks to produce. By early January 1943, they had completed 3 jungle-side cylinders, light green, dark green, and brown. Berman mounted them on his experimental printing line and ran the first test on January 9th. The fabric moved through at 70 yards per minute. The colors printed beautifully. Registration was perfect within 0.02 millimeters. Then the fabric exited the dryer and Berman flipped it over to check the reverse side. The beach pattern side was green, completely green. The jungle ink had soaked through the herringbone twill and obliterated the tan base color. They'd solved registration. They'd solved speed. But they'd made the bleeding problem worse, not better. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Berman spent 4 days analyzing ink penetration depth using microscopic fabric cross-sections. The problem was pressure and speed. At 70 yards per minute, the squeegee inside each rotating cylinder pressed ink through the mesh, with enough force to drive it completely through the fabric. Slower speeds reduced penetration but defeated the whole purpose of continuous printing. He tried thinner inks. They ran and feathered, destroying pattern definition. He tried barrier coatings applied to the fabric before printing. The coating made the fabric stiff and reduced breathability, making uniforms unwearable in tropical heat. The solution came from somewhere unexpected. Rose Kellner, the Philadelphia flat-screen printer, had been transferred to Camden as a quality control inspector. She'd been examining Berman's rejected fabric when she noticed something. The bleeding wasn't uniform. Areas where the herringbone, twill pattern created thicker fiber density showed less ink penetration than areas where the weave was looser. She showed this to Berman. He looked at it for maybe 10 seconds before he understood. The fabric itself was the variable. Standard herringbone twill used for marine utilities was woven to optimize durability and cost, not ink absorption characteristics. What if they specified a tighter weave pattern specifically for camouflage printing? Berman contacted Riverside Mills, asked if they could weave herringbone twill with 20% higher thread density. The mill said yes, but it would increase fabric cost by 15% and reduce production speed at the looms. Harrison approved the change immediately. 15% cost increase was nothing compared to solving the bleeding problem. Riverside delivered the first rolls of dense weave herringbone on January 28th. Berman ran the test that afternoon. Same ink formulation. Same printing speed. 70 yards per minute. Same squeegee pressure. The fabric came out perfect. Jungle colors stayed on the jungle side. Beach colors stayed on the beach side. Registration held within specification. Quality was better than anything flat screens had ever produced. They ran the machine continuously for 8 hours, printed 560 yards of fabric, enough for 93 complete uniforms. 0 defects. 0 rejected material. Production rate, 11 uniforms per hour, compared to flat screen's rate of 0.06 uniforms per hour. That's an improvement of 18,000%. Not quite the 90% improvement that marketing departments love to claim, but 18,000% improvement in production speed while simultaneously improving quality. The first production rotary printing machines shipped to Philadelphia and Riverside Mills in March 1943. By April, both facilities were printing frogskin fabric at rates exceeding design specifications. Philadelphia alone produced 12,000 uniforms in April, more than they'd produced in the previous 6 months combined. The Marines received their first rotary-printed camouflage uniforms in May 1943, just in time for the new Georgia campaign. After-action reports noted significant reduction in sniper casualties compared to Guadalcanal. Whether this was due to better tactics, improved training, or effective camouflage is impossible to determine. Probably all three, but production numbers tell their own story. By July 1943, 3 mills running 6 rotary printing lines were producing 42,000 frogskin uniforms monthly. By war's end in August 1945, American mills had manufactured over 500,000 sets of camouflage utilities using rotary printing technology. Berman never received public recognition. The War Production Board classified his work until 1978 because rotary screen printing technology was considered strategically valuable. After the war, he went back to printing theater backdrops. He died in 1967. His obituary in the Brooklyn Eagle mentioned his printing business, but nothing about camouflage or the war effort. Rose Kellner, whose observation about fabric weave density solved the bleeding problem, returned to Philadelphia after the war and worked at the Quartermaster Depot until she retired in 1971. Nobody ever knew she'd contributed to one of the critical manufacturing breakthroughs of World War II. The real legacy wasn't technology. Rotary screen printing had existed in Europe for years before Berman adapted it. The legacy was the principle, the same principle that appeared in every major industrial breakthrough of the war. When standard methods fail, look at the actual physical problem, not the theory, not what should work. What actually happens when metal meets fabric at 70 yards per minute? Engineering perfection doesn't win. Wars. Practical solutions implemented fast win wars. Berman's rotary printing line wasn't elegant. It was a collection of borrowed ideas, improvised parts, and brute force problem solving. But it worked. And sometimes that's the only thing that matters. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.